binaries, amplitudes, and EFT. Please.
Thank you so much, Gabriele, for the introduction. Let me join the other speakers and thank the organizers for putting together this meeting, and also complaining about the fact that we are not in sunny California these days. But anyway, hopefully next year. Yeah, so I will tell you about this work I've been doing the past couple of years on trying to apply amplitudes to spinning binaries. Okay, so for an introduction, I was fortunate enough to speak after Justin, so I just have to refer to his beautiful broad talk. But the idea is that we want to exploit the techniques of scattering amplitudes to solve the two-body problem. There have been many talks about the subject and about spin, even though it's again a very active topic. There have been several nice, important papers in the last 6 or so months. There aren't many talks, so we have this too. Okay, so this is how the talk is gonna be. In the first half, I will review the work up to spin squared that is based in a paper with Svibern, Radu-Roivan, Xiaoxuan Shen, and Mao Zheng that we published a year and a half ago, and in a paper that we with Dimitris Kosmopoulos we published earlier this year. By the way, to those in the audience who are hiring, Dimitris is in the market this year, and he's great. But if you want him, you have to move fast because he's already receiving offers. So that's the advertisement. Then in the second half of the talk, I will tell you about these new results for spin cube and spin to the fourth. And this is based on work in progress with SV, Dimitris, Radu, and Fei Teng. I'm being optimistic and saying that it will be out this month, but the year is ending soon, so I can only guarantee that it will be out in this decade. And finally, for our outlook, we are working already on spin to the fifth. So yeah, let's go to this quadratic in spin. Sorry. Okay, give me 1 second. Yes, there we are. So this is a story about applying amplitudes to black holes. So we will use, we used an EFT to extract the dynamics. So how do we compute full quantum field theory amplitudes? We start with a Lagrangian, and I mean, to amplitudes people, this is a bad word, but it's not so bad. We only wanted to compute the Compton amplitudes. There are only 4 diagrams. It's okay. You should forgive me for doing that. Then we use that Compton amplitude as building block to build one loop amplitudes. And then we got ourselves our full theory amplitudes. On the other side, we will start with this effective field theory. And we also use some Feynman diagrams to compute my EFT amplitudes. Then we do a matching procedure to obtain a Hamiltonian from which we can describe the dynamics of the binary. We solve the equations of motion, and then we got ourselves some observables. So I will consider for the Lagrangian this. I will represent my spinning black holes using a symmetric Trechler rank S tensor fields. In the Lagrangian, it appears the covariant derivative, and that is given in terms of the spin connection and the Lorentz generator. Then, because I will have this product of the Lorentz generator with the polarization tensors, I will obtain my classical spin with this kind of relations. So that product of polarization tensors with Lorentz generators give me the spin tensor. And I can then relate my spin tensor with the with the spin vector, which is the one appearing in the final results. Okay, and that's the minimal part of the Lagrangian, the minimal coupled part of the Lagrangian. But then we can also use an effective Lagrangian that encodes the higher spin interactions. This was introduced by Porto and Rothstein and then systematized by Levy and Steinhoff, like Justin mentioned. So we know that to tree level, this will reproduce the curved black hole for certain values of the Wilson coefficients. So what about the loops? If we look only at the first term, which is like a spin-induced quadruple, and that operator there is an analog of the Pauli-Lubansky vector. That is the dual of the Lorentz generator. Then we can use that Lagrangian, which is the minimal couple part plus the spin-induced quadruple. From this Lagrangian, we deduce final rules, we go compute Compton amplitudes, and then we paste them into cuts and use unitarity to extract the one loop amplitudes. Okay, then we have to go to the EFT to get our matching. So we adapt the EFT that was introduced by Chang, Rothstein, and so on, so that it's able to also describe the spinning effects. We consider it potential like they did, but that's given, and it has the same form to contain the long range interactions. But now it's given in terms of all of the possible spin operators that will be relevant to classical level. Okay, so in that theory, we have our final rules. We go compute a scattering amplitude. Once we have the amplitude in the full theory and the amplitude in the EFT, we equate them. That is called a matching procedure. And from that, we can read off the coefficients of the potential that was appearing in the EFT. Yeah, so from the information that we have from the full theory, we will fix the coefficients that will enter the potential and the Hamiltonian that will be describing the binary. So we have that piece that comes from full theory, and we have the iterations, and the EFT subtracts everything that will be divergent. So, okay, we have a Hamiltonian that describes this classical system. What do we do with that? So one thing we can do is get equations of motion and solve them perturbatively to obtain our observables. For example, this delta P and this delta S. Those 5 pages appearing there are the ancillary file that we included in one of our papers. What we noticed then is that you can collapse all of that information into a one-line formula in terms of that object, chi, which is like an Eikonal phase. I say like an Eikonal phase because I'm not saying anything about the exponentiation of this. All I mean is that this is a Fourier transform to impact parameter space of the amplitude, of a relevant part of the amplitude. And acting on that object with a differential operator, I can obtain observables, which is very much analogous, and in the non-spinning case, exactly what happened using the Eikonal approximation. So that's what I mean by an Eikonal phase-like object. Okay, so then I know that by looking at the important part of the amplitude, which in this case is the triangle, the part coming from the triangle scalar amplitudes, I can reproduce the dynamics simply by acting in some way on my amplitude. So there is a direct link between my amplitude and the dynamics. And that's what we did up to spin square. Good. So once we have these amplitudes and this Hamiltonian up to spin squared, we had to check that it was right. So we went to compare with the overlapping parts of the Hamiltonians that were in the literature. Because Hamiltonians are hard to compare because they are coordinate dependent. We instead took the Hamiltonian yes and produced an amplitude using the EFT, and then we compared the amplitude, which is a gauge invariant object. So we did this for the post-Newtonian, the next to leading order spin squared Hamiltonian that was produced by Michel and Jan, and that matches. And also for a test body limit Hamiltonian by Hinderer, Steinhoff, Weiss. I think I'm missing an author there, sorry. And also there was a concurrent paper using post-Minkowski and EFT with spin by Liu, Porto, and Yang. We have also a match there. And finally, we can mention that this reproduced the aligned spin scattering angle when we specialized to black hole that was produced by Guevara, Oshiro, and Weiss. So there are lots of checks that were performed for these results. It's worth mentioning that the first three also included the Wilson coefficient, the CES2, which is the spin-induced quadrupole. So in these three cases, this is not only for black holes, but also for to describe generic bodies. Okay, so then I can move to our new results for cubic and particle spin. So as I said, this approach was quite successful for quadratic in spin. So using this Lagrangian, we got quite far. So one should feel tempted to add the next term in the effective theory, Lagrangian, and go compute that guy. So the spin-induced octopole. Okay, so just to show you something that happened, let me tell you, we can compute, we can start from Lagrangian, go compute an amplitude, and from that get an angle. This is just for the aligned spin. It's not the only thing we can do, but it's the simplest, and this will be enough to make my points. So we did that. So from Lagrangian, go to angle. Good. I grab that Lagrangian, and I go compute the scattering angle, and I specialize to the black hole limits to compare to GOB. And the results don't match. Yes. So what happened? It's difficult to see like this because we are kind of blind there. But if I check the result with Wilson coefficients, if I don't go to the black hole limits, and consider only the M2 part, which is the first line here, then I get that result. So I compare to a result that was produced by Justin. I thought he was going to mention something like that in his talk, but then he had no time after the review that he did. But basically, he uses geodesics in Kerr to compute these observables, and he's able to do it, including for test bodies that are not necessarily black holes, but generic bodies. So he's able to produce this kind of aligned spin angles. And then we see that the result that we have matches almost everything, but it's missing that piece. So we are missing that piece because we were missing terms in our effective theory. Now, I see there's something in the chat. Okay, is that a question or?
No.
No, please go ahead.
Okay, sorry. So, yes, this H2 guy had already appeared in our first paper, and this is somehow a minimal coupling in the sense that it has a minimal term of derivatives there. It has been studied before, but at 3 level, and even at 1 loop, up to spin squared, the amplitudes that it will produce, they are equal to the amplitudes that will be produced by the other Wilson coefficient, the CES2. So then we decided to leave that in favor of the CES2. But in this case, when you go to spin to the cube, they are no longer the same. They produce no longer the same amplitudes. So if we stick with this H2 and the ES2, we see that we are able to reproduce the GOB result. So because we are doing an effective field theory, what you have to do is include all the operators. And before we didn't do it because they were just producing the same. So so it didn't matter that we disregard that one. But in this case, it matters. So what we have to do is leave no operator behind. So we go back to consider this. We compute our amplitude, our angle, and then we obtain this result. Now, in order to match the results, we need that H2 to be equal to 1. This is this is something that it's not coming exactly from the matching to the Kerr black hole, but we have there's a clue as for why this kind of operator should be valued 1 in this paper. I was Kunst, the author that I was missing. So in a word line analysis, they find that this kind of couplings should have that the prefactor, so like a Wilson coefficient in front of these operators being actually fixed. So we are not sure yet how to understand this in our formalism within our EFT. That's something we are still working on. But okay, I can go compute my Quintio-in-spin amplitude, including all of my Wilson coefficients. So this is what I get. This is one first new result, Quintio-in-spin with Wilson coefficients, so describing generic bodies. Good. So I have my amplitude, and how do I check that it's right? First of all, in the black hole limit, it matches this very recent result, 3-week-old result by Chen, Chang, Huang, and Kim. So that's a good check. Then I can check that it matches the aligned spin angle with or without Wilson coefficients that were produced by GOB, that's Guevara-Cherov-Bynes, the paper from 2018, or from Justin in an unpublished result, but that contains the Wilson coefficients. That's another pass check. And also, in the black hole limits, we check that it matches an Eikonal phase-like object that was obtained from Kerr geodesics by Justin Bynes. This is still unpublished, but our result looks like this. And let me emphasize that this works for generic spins. This is in no way confined to just describing aligned spins. So that's another check that our result is passing. Okay, so let's go to quartic in spin. That's the Lagrangian. We have to add the next one in the effective Lagrangian, so CES4, and also in analogy with H2, we have this H3, which substitutes 2 of these like spin operators in favor of just a Lorentz generator, like what happened with the H2. Yes, so we have the amplitude for quartic in spin. I don't show it here because it's lengthy. The shortest part is that A1 to the fourth, which is only 6. It has only 6 operators, but also the cubic in one and linear in the other. It has, I think, 9, and the next one it has 13. I think they are not all independent, but it is lengthy and it's not very illuminating. We have to check.
We have 10 minutes.
Good.
10 minutes.
I need less than that. So we have to go check our quartic-in-spin amplitudes. And the first, the same with as with the cubic, we check the black hole limits, and the parts that we have checked so far, they match the amplitude by CCHK. So that's good. We also have a match to the aligned spin angle without Wilson coefficients, which is the GOB. And for the Wilson coefficient dependent checks, we are still working on the checks, but they are looking good. Okay. The goal, as Justin mentioned a few minutes ago, is going to Quintic-in-spin. And the reason why this has been, well, one of the reasons why this has been a lot elusive in the past is because using these bootstrapped amplitudes, you run into these spurious poles. But we are working with a Lagrangian. And that was, from the get-go, one of the motivations to work with the Lagrangian. There are no spurious poles to be encountered there. So we have that Quintic-in-spin amplitude, just the A1 to the 5th, from the Lagrangian that we are seeing in the screen. It's just the next term in the effective theory that corresponds to the Levy-Steinhoff word line, so the one that is 1-to-1. And in analogy, we have some H4 that I'm not showing explicitly here. We have the amplitudes. We are still working on checking against wherever we can check. And we are also running to get the other pieces like A1 fourth A2 and A1 cube A2 squared. But okay, we are working on this Quintic-in-spin. I'm not sure if we are putting any of this on the upcoming paper, but we are currently working on this. Good. So this brings me to my conclusions. So we have developed a framework to compute or to describe spinning binaries from amplitudes and EFTs. So not only our non-relativistic EFT that allowed us to do a matching and go to a Hamiltonian, but also mean the EFT describing the non-minimal coupled terms in spin. We have new results for spin cube and spin to the fourth, the amplitudes, and also an Eikonal-like objects, Eikonal phase-like objects that describe generic bodies in the sense that we have that for the result with Wilson coefficients. And then our outlook and work in progress. We want more spin, so spin to the 5th. We are working on that. And we are also going to 2 loops, be it conservative or also including radiation. And we also want to understand more about the double copy of the Compton amplitude. It's just going to this high spin. The Lagrangian starts being cumbersome. So it would be very useful to have a double copy description of it to make it easier. And that's me. Thank you.
Thank you very much, Andres. I have just a very simple question myself, comparing with the previous talk. I mean, are we sure we are describing curved black holes in this way, or is this still something you have to find the matching with?
Yes, I am not. I'm not completely sure. So we are doing an effective field theory description. We have Wilson coefficients, and in the end, we need information that comes from the black hole, like Justin said in the previous story, so that we can fix what the Wilson coefficients that we are including in our theory and what are their values. So
when you were saying we match the black hole limit, was this a check against a GR result, or?
Yes. So when I say we match the black hole limit, or in the black hole limit, what I mean is this reproduces the result from GOB. And then I consider that GOB is black hole because of the evidence that comes from applying not geodesics, but for a multipolar test body, but considering the test body scattering over a Kerr background. So that is what I mean by the black hole. So GOB plus the evidence that comes from GR that GOB is actually right.
Okay, I see that Justin wants to intervene.
Just a comment. Yeah, yes. I definitely don't disagree with anything Andres just said. But about whether or not GOV describes black holes. And that's just for the align spin part, which is easier than the processing. Let me just make a long story short and refer you to the paper by Niels Simonsen and myself from September 2019, where this had nothing to do with the scattering gravitational waves of Kerr yet, which came later, started with Bautista, who, by the way, is a grad student collaborator of mine who is on the postdoc market. He talked yesterday. Also see the Slack gravitational waves channel just now. Rather comparing with actual self-force calculations from the self-force community that already existed. So see, and let me just summarize with, you can almost completely constrain this align spin scattering angle with existing self-force results, but not entirely. And anyway, GOV is consistent with these self-force results. And another ad for my other best grad student collaborator who's on the postdoc market is Mohammed Halil, and again, see the Slack. Yes, Andres.
Yes, so, but that's for spin to the fourth, right? Because for spin cube, you also have a result which is non-aligned.
Yeah. Spin cubed is right. Spin cubed, it's a black hole, no question.
Yeah, so at spin cube, GOB is black hole.
Yes.
Okay, at spin to the fourth, there might be more to say about that. There are also quadratic incurvature operators that might add to the complexity of the problem, etc.
But it's consistent with.
Yes, so far GOB is consistent with the black hole, and we are totally consistent with GOB in some choice for our Wilson coefficients that we are including. Yes, that's the answer to your question, Gabriele.
Okay, I understand. Thank you. Let's see other questions.
Yeah,
once because we are late.
It's already been Lagrangian prone for spin 5/2. So how does your calculation compare with that?
Sorry, can you repeat the question?
Henrik Johansen and collaborators already did spin 5/2 from the Lagrangian.
Yes.
How does your approach compare with that result?
No, we haven't finished that comparison. I will have you know this result is just a couple of days old, and we've been a bit busy with the conference, but yes, that is one thing I'm doing next week. So stay tuned.
We have time for one more question. Oh, did you?
Okay, one last question.
No.
Is there another question?
Okay. I'm a little confused about the status of the quote unquote conjecture. So I think we probably all agree that if we knew the Wilson coefficients for a black hole, it would no longer be a conjecture. So which coefficients are in question? The last two talks, I think, both implied that, right? Did I miss something?
There's both ones as well, right?
Well, I just want to know which couplings, which Wilson coefficients are not believed to be known for a black hole.
So that might be r squared s to the fourth.
So I was under the impression all the r squareds were 0. Is that not correct?
Sorry, go ahead, Andre.
You can take this one, Justin.
Yeah, there are definitely those kinds of claims recently within the last year that all of the love numbers, all orders in spin are 0.
Right. So, but I see. So
it's just not immediately clear to me how maybe definitions of these love numbers used there relate to Wilson coefficients in your favorite QFT Lagrangian or world line action.
I think for the mapping may be non-trivial, but if they're all 0 in one, then they're all 0 in the other. So how you break them up, I don't think really matters. So if you believe that result, I forget who the author was. It's a postdoc at Princeton. I don't remember his name. I think if you believe that result, then they're all 0 in the EFT as well. It's true that in principle, you might have to do some work into a one-to-one map, but I think if that result is right, then those are all 0, and then.
Well, there are issues. There are issues like, again, what is your favorite formulation of this effective theory on a world line or in a QFT? And simple things like in a world line action, if you were to use a Lagrangian directly, or if you were to use, say, like this mass shell constraint, roughly speaking, something gets squared between those two, a Lagrangian or a mass shell constraint. And so if one of them had no Riemann squared spin to the fourth terms, for example, the other one would, because the Riemann spin squared term, if that gets squared, that's a Riemann squared spin to the fourth term.
Yeah, but I think, but one thing, there's a physical observable which is invariant, and if you don't have any, if you have any local contribution to the quadratic curvature in one, then physically you can't have it in the other, right? In any formulation of the world line, right?
I'm not sure I followed that. We should continue.
Okay, we can continue.
Perhaps you can keep discussing that on Slack or later. So maybe we should thank the speakers now, and I let the organizers decide when they want to reconvene. It's still 10 or a little later.